So Dalton's law is that the total pressure is the sum of the individual pressures. So the total pressure is the sum of the individual pressures in a system. So suppose I've got a container, and inside my container I've got hydrogen gas. And the pressure of that hydrogen gas is 35 kPa. And also inside this container is oxygen gas. And the pressure of the oxygen gas is 25 kPa. And let's just give a third gas. Well, let's just stop at second gas. And the second two gases, the total pressure inside the system would be the addition of just these two gases. Now, if there's a third gas or a fourth gas, you just keep adding them up. So the total pressure inside the system is 35 plus 25, and that's going to equal 60 kPa, okay? So the problems in the book use Dalton's law in what's called a wet gas. A wet gas is a gas collected over water. Or another way of saying is that a gas that contains water vapor. So very often what we'll do is, in science, is we'll have a sink, and in my sink I have water, and then I will do my experiment and have a container over the water to capture my gas. So suppose I've got my beaker over here, and my beaker has a top on it, and then I'll have a tube running into here, and so the gas will come bubbling out my tube, and I can collect my gas inside there. So that's what I usually do when I run an experiment. I collect my gas over water, all right? And we would have done this if we would have been in school. So my gas is going to exert some pressure. And let's just say the pressure of the gas is, I don't know, 45 kPa, all right? Well, there's another gas in there that you may not have realized, and that is water. Water evaporates. We know this. Hot water evaporates faster than cold water. So some of my water will evaporate. And so I will have some gas pressure due to the water, okay? That's called a wet gas, where there's water vapor mixed in with your own gas. So how do we find the water vapor? Well, we need to know the temperature, because like I said before, hot water will evaporate more than cold water. So we need to know the actual temperature of the water. And so in my problem, we must be told the temperature of the water. So in this problem, I'm going to say that the temperature of the water is, let's say, 35 degrees Celsius, okay? Then what you have to do is you have to go to page 360 in the book, or Appendix O, to go to a vapor pressure table. That's Appendix. Okay, so on page 360 in the book, or Appendix O, you will see a table, and you will see that when the temperature of the water is 35 degrees Celsius, it exerts a pressure of 5.6 kPa. So now I know that my pressure is 5.6 kPa. So then the total pressure of the system is 45 plus 5.6. So the total pressure is 50.6 kPa. Now, very often we want to know the volume of the gas, okay? So I want to know how much volume my gas takes up, okay? So I'm just going to draw this picture bigger on the next page. So the water vapor takes up some volume. So what I want to do is I want to remove the water vapor so that only my gas is left. Now we have to do that mathematically. Okay, we can't actually do that in reality, but we can do it in mathematically. So what we can do is say, very often what we do know is we know the total pressure. So suppose that the total pressure was, and this is going to just be a new problem here. Suppose my total pressure was 85 kPa. And I want to know the pressure of my gas, okay? And I know that the volume of this container is 50 milliliters, okay? The volume of that space right there is 50 milliliters. And I would like to know what the volume of the gas would be if it didn't have the water vapor. Because, like I said, the water vapor is taking up space, okay? If the water vapor wasn't there, the gas would take up less volume. And so my volume would be smaller without the water vapor. So V1 is with the water vapor. V2 is without. Okay? Another way we can say this is V1 is wet because it's got the water vapor, and V2 is dry. So V1 is 50 milliliters. V2 is what we are trying to find. I know that the total pressure is 85 kPa. Okay? What is the pressure of just the gas? This is a mistake right here. Because the total pressure is going to act as P1. The pressure of the gas is going to act as P2. Okay? So let's find the pressure of the gas. Well, I need to know the temperature of the water. Okay? So the temperature of the water is going to be, let's just do 40 degrees Celsius. Okay? At 40 degrees Celsius, the pressure of the water is 7.4 kPa. All right? So to find my pressure of the gas, I'm going to take 85 minus the water vapor pressure. And so the pressure of my gas is going to be 85 minus 7.4. Okay? That's my P2. So I have now everything I need to solve for my V2 dry gas. So I'm just going to rewrite all the pertinent information. So I've got my V1, I've got my P1, which is 85, and I've got my P2. Okay, so I have everything that I need in order to solve for V2. All right, so here we go. P1 V1 wet is equal to P2 V2 dry. The P1 is 85 kPa. The V1 was, I forgot, 50 mils. The P2 was 77.6. And then the V2 dry, we're going to calculate. So we're going to solve for P1 V1 wet over P2 will equal V2 dry. Now let's plug in our numbers. So 85 kPa over 77.6 kPa times 50. And so when I do the math, the kPa's cancel. And I get 54.7 kPa. And here's the reason why the volume goes up. I misspoke before. If the pressure goes down, the volume goes up because it's an inverse relationship. So as pressure decreases, volume increases. Okay, and you can think of this when you think of a balloon. If you've got a big old balloon and you squeeze that balloon from all sides and you make that balloon smaller, what's happening to the pressure inside there? It's going up. So if your volume gets smaller, your pressure goes up. Okay? I'll do another example of this in the next video.